They called Ukraine's drones toys, until those toys turned an entire North Korean battalion into craters. How do you fight an enemy you can't see, can't jam, and can't outrun? Stay with us. The answer isn't firepower, it's synchronization. We'll unpack the hidden coordination that makes a swarm deadlier than a missile strike. Before we move on, please take a moment to subscribe to the channel and like the video. How can $140,000 worth of homemade UAVs silence radars that cost billions to develop? The answer begins in total silence. As dawn broke over the Eastern Front, 70 compact drones lifted from a line of makeshift launchers. Each carried a simple device, an electromagnetic transmitter built out of scavenged radio parts, bolted to a carbon shell light enough to glide on minimal thrust. They climbed no higher than 60 meters, weaving through farmland and tree cover on zigzagging routes that made their radar profiles flicker like stray ground clutter. This small, scattered fleet was about to blind two of the most advanced defense systems in the world. The mission started in electromagnetic stealth. Ukrainian software engineers had loaded unpredictable waveform patterns into every drone, so the signals they emitted would never line up with standard radar scanning rhythms. Federal-grade systems like the S-500 and KN-06 depend on logic loops to filter noise and single out genuine aircraft signatures. By sending irregular pulses that slipped between those loops, the drones snuck inside the detection range without setting off alarms. Operators on both ends of the border watched clean, empty screens, unaware that multiple jammers had already crossed into the field of view. When the transmissions began, nothing sounded mechanical or consistent. Each drone switched its frequency and amplitude at uneven intervals, producing bursts that looked on the screen like light cloud interference. In a matter of seconds, the defense consoles lit up with hundreds of new echoes, all moving in erratic directions. The radar processors couldn't reconcile the noise, so the computers filled the gaps with phantom squadrons. Commanders saw formations that didn't exist, aircraft that accelerated too fast, or reversed course for no reason. Every adjustment to filter the unknown signals only multiplied the chaos. Traditional suppression of enemy air defense missions depend on large aircraft, anti-radar missiles, and coordinated airstrikes. A single sortie can cost tens of millions of dollars and still risk pilots and equipment. Here, that cost was replaced by ordinary hardware. Ukraine's technicians assembled their jammers from consumer broadcast amplifiers, salvaged coils, and printed circuit boards stripped from civilian radios. The range of each individual unit was limited, but synchronization made up the difference. A small block of code told each drone when to start and stop transmitting, staggered every 4 seconds. This timing flood buried radar sweeps in mismatched signals that jammed not only detection frequencies, but also range-finding channels. Inside the control rooms, the effect was immediate and disorienting. Russian and North Korean crews tried to reset their scopes, believing the visual distortions to be static discharge. The next moment, their monitors filled with shifting blips, stretching across entire sectors. Some systems auto-initiated countermeasures against targets that weren't real. Others crashed altogether. Communication links froze under the weight of conflicting data, breaking coordination between missile batteries. For the operators, it wasn't an explosion, but a kind of blindness. Screens that once defined enemy movement, now showing dozens of looping illusions. By the 2-minute mark, the electromagnetic field was saturated. The drones continued to drift in their erratic routes, layering interference until the entire radar network went dark. The silence inside those bunkers was a new kind of defeat, weapons rendered useless by noise. For the technicians who built the swarm, the experiment had proven its theory. Chaos in the spectrum could overpower precision systems that took years to refine. Overhead, the jammers began shutting down one by one, conserving power. Each unit had cost less than a laptop, yet together, they had erased billions in enemy infrastructure. With sensors blinded and communication lines scrambled beyond repair, a second wave was already moving into position. Drones that wouldn't just jam signals, but hit their targets in complete silence. After the radar blackout, the front looked untouched. No smoke, no motion. Only the silence that follows a system collapse. But dozens of meters above the ground, compact engines whispered across the valleys. The second phase had already begun. 150 modified aircraft, built from salvaged drone frames and coated in carbon fiber dust, moved as if tethered together by invisible threads. They kept to tree lines and trenches, slipping past outposts whose instruments were still blind from the jamming storm. There were no control signals guiding them now. Each drone followed a preloaded map based on terrain data, adjusting to local coordinates without satellite feedback. By switching to passive routing, they vanished from every known detection grid. Every hull carried a 20-kilogram concrete penetrator warhead, small enough for the drone to stay agile, but heavy enough to punch through reinforced shelters or disable tanks parked under camouflage nets. Builders had rigged local, inertial sensors so that when one drone hit an obstacle or reached a high point on its path, the next adjusted altitude automatically. Coordination wasn't handled by a pilot or operator. It emerged from algorithmic timing written into the flight code. Engineers called it cooperative autonomy, hundreds of individual units acting like a single body without ever speaking to a command tower. The blackout had created perfect conditions for stealth. With radar frequencies still saturated and communication networks cycling through restarts, the swarm moved in complete absence of electromagnetic chatter. Each IFF beacon, every radio request, had gone dark in Phase 1. That silence now functioned as a shield. The moment a sensor looked for a signal to trace, there was none. The drone's only inputs came from passive GPS correction layers derived from local field beacons. Simple radio anchors built by Ukrainian volunteers using recycled transmitters from farming equipment. At minute 6, the first wave split into smaller cells. They followed separate valley floors at a fixed speed of 80 kilometers an hour. The software calculated likely resistance points by cross-referencing stored elevation data. When one route showed open terrain, part of the cluster peeled away to exploit the gap. In those few seconds, human oversight would have slowed the process, but no humans were involved. The guidance network assigned impact coordinates dynamically, aligning warheads so their detonations overlapped in patterns that magnified ground shock. One cluster, initially bound for a radar outpost, received updated trajectory data from its onboard camera array. Heat signatures revealed an S-500 system sheltered near a fuel depot. The swarm's logic recognized the combination of energy emissions and rerouted 5 units. 30 seconds later, the first explosion ruptured storage tanks, feeding a chain reaction that ripped through munitions buried beneath the depot. Debris and shockwaves tore at adjacent sites, collapsing supply bunkers that hadn't yet been evacuated. For observers outside the blast radius, the attack looked simultaneous, multiple strikes firing from nowhere, because the timing sequences were designed to synchronize within milliseconds. The absence of centralized control meant there was no master signal to track. Every drone was its own command post, containing everything it needed to complete the mission. Jammers couldn't lock on because there was nothing constant to disrupt. Even electromagnetic pulses failed to sync against such scattered timing. When defenders tried to broadcast interference on expected frequencies, the swarms had already cycled to new internal clocks. While the drones shredded front positions, 15 R-360 Neptune missiles entered the area at treetop height. Their terrain-following radars remained unaffected by the earlier electronic chaos since Ukrainian command had already cut friendly transmissions before launch. The Neptunes used the natural contours of the Earth as a guide, emerging over ridges with barely a meter of clearance before striking command bunkers precisely marked by the swarm's onboard mapping code. The strike wasn't driven by brute force. It worked because every element moved in rhythm. Hundreds of independent units, syncing through code, timing, and shared purpose. That coordination turned scattered drones into a real-time machine of precision. Each circuit, signal, and rotor belonged to something bigger than itself. Cheap distributed warfare now rivals the power of state arsenals, turning engineers into generals. The boundary between invention and defense strategy is fading fast, so the question shifts from who has the most weapons to who can make machines cooperate. When enemies fight without formation, what does deterrence even look like anymore?